Saurabh received his bachelor's degree from IIT Delhi, where he received also a big shiny gold medal, which says the President's Prize. I guess it means he's the top students from IIT Delhi. So I don't know if you're talking about IIT Delhi here. It's a big achievement. And since then, he's been working on vision problem and lately working with robotics as well. So Saurabh has done many work on RGB data. So many years ago, there was a Connect sensor came out, and that was the first time that vision made it to public domain knowledge. Before we had to explain what computer vision is to our relatives, and nobody knows. Now Connect came out, and everybody knows computer vision. Now, of course, the deep learning has taken over. Everybody knows computer vision. But Saurabh has worked on many areas in the RGB data area, which is very relevant to robotics. Talk about how to transfer learning from images, which are RGB, to that sensor data and transfer information back and forth. We also worked on a lot of semantic recognition of actions, worked on the image capturing. But most recently, he has worked on this area, which is very challenging, which is combining vision, planning, and navigation together. This is work with circular lane and also with multi-modal. And this is probably, I think, the most interesting topic that going forward for many of us. How do we think about vision, planning, and learning all in one domain rather than separate domains? So today, the talk's going to be about a representation for visual guided actions.
Thank you. Thanks for the introduction. Thanks everyone for coming. And yes, I'm going to talk about representations for visually guided actions. And I'll start by first taking a look at typical robotics pipelines. So if you consider a task, let's say navigation, where we want the agent to actually move around, and we look at what a typical solution in robotics looks like. It starts out by using a vision module to go from observed images into a 3D reconstruction of the world, and then using a path planning algorithm for computing trajectories for the robot to actually move. We can also look at example in manipulation, where let's say the task is to grasp an object, and this also starts from you have images as input, we use a vision module, compute a 6-DOF pose for the object of interest, and then use a motion planning algorithm to compute a grasp and then execute it on the real world. So now if we think about representations that are used in robotics, in classical robotics, they essentially comprise of these explicit, handcrafted, completely geometric descriptions of the world. And not only are these descriptions extremely hard to compute by themselves, so estimating these representations from image observations is hard to do accurately, but at the same time, this is often the primary bottleneck in why when we try to run these systems in the real world, things don't work. Because the vision module fails, it does not give you the accurate pose, the downstream planning algorithm does not know how to use a noisy pose, and so forth. So there is this disconnect between this representation essentially bottlenecks the performance that one gets at the end of the day. This very naturally motivates learning-based robotics, where the game is to go from pixels to actions in an end-to-end trainable fashion. As shown by work in context of video games at DeepMind and in lots of robotic contexts by people all over the world. And over here, the nice thing is that representations are implicit, but more importantly, they are learned end-to-end for the task that we care about. For example, if it's grasping, then you're actually learning representations which will be useful for grasping, and so forth. But then this comes with the caveat that such systems typically ignore the structure of the problem that they're trying to solve. So it's, at the end of the day, just a deep network which you train for the task, and we throw away the structure that exists in the problems, which might make solving some of these problems harder. And this is evident from the fact that results with these kind of techniques have typically been only shown in relatively simple short horizon tasks, which are often only 2D in nature and not even 3D in nature. They, at the same time, require large amounts of data for training and result in behaviors that are extremely specialized and do not generalize to new tasks or environments. And this is essentially what motivates my talk today, where I'm going to argue for representations for robotics which try to find a middle ground between these two extreme views of the world, where representations can actually be task-driven, such that they can be learned for the task that we are trying to solve, but at the same time, appropriately leverage the structure that exists in the problem that we are trying to solve. I'm going to talk about these representations in multimodal context with 3 projects, one on robot navigation, where I'm going to show how we can learn task-driven representations for space. Then I'm going to talk about structured representations for scene understanding, focusing on objects. And then finally talk about how we can leverage multiple modalities in context of robotics, where we have a variety of sensors that we would want to use on a robot. So let's actually go into this robot navigation problem. So the problem that we are going to tackle is we have a robot which is equipped with a first-person camera, as you can see on the left. It has been dropped into a novel environment that it has never been in before. And then what we want this robot to be able to do is to move around. And what do we mean by move around? Is we want it to go to, let's say, a particular point in space, or find an object of interest. Let's say, go find a chair. And actually, let's now go back and see what are the problems with the representation a classical robotics pipeline would come up with. So the representation that we are talking about here is a geometric 3D reconstruction of the environment. And I would argue that this suffers from two key problems. One, it is over-complete representation, in the sense that we actually may not need the entire reconstruction of the whole environment to be able to, if we only care about is moving around. So I don't need to know what is the precise structure of the top of this podium if I only cared about walking around. So in this sense, we may actually be solving a harder problem than what is necessary to solve the task. At the same time, such a representation is also incomplete because it is purely geometric and does not have any semantics associated with things. And semantics over here come into play in lots of different ways. There could be navigational affordances. So doors have a particular affordance that they allow us to go from one room to another. Hallways have a particular affordance that they allow us to go from one part of the building to another faraway part of the building. And being purely geometric, we are kind of throwing away all of this information. At the same time, we make this extremely strong assumption that nothing is known till you have actually observed it. So a classical system will actually need to have observed every place before it can, it does not make any speculations about how the environment may actually be laid out. And there is failure to exploit experience with similar past environments. So I've never been to Penn, I've never been to Levine Hall, but I've been in plenty of office buildings in different contexts, and I know what typical office buildings are laid out, and that might actually help me navigate around in Levine Hall without actually having visited every nook and corner to begin with. We can also look at one of these recent learned navigation systems. So this is something that appeared earlier at ICRA this year, where the representation was being computed using a feed-forward neural network. So again, it's something that is trained end-to-end for the task of moving around. And this suffers from this problem that because you do not have any memory, the agent cannot specialize its policy to a new environment that it comes in. So it knows about generically how office environments are laid out, but when it comes to Levine Hall, it cannot specialize its representation to the exact specifics of what Levine Hall looks like. And this results in problems like you cannot do mapping, you cannot actually do any kind of backtracking. If you think there are two doors and doors are useful for you to exit from a room, you go to one door and you find it locked, there's no reasoning that will allow you to find another door, and so forth. So representations such as these are limited by the very design. And this is in strong contrast with the evidence from psychology, where Tolman was trying to study navigation behavior of rodents like rats. This was done at UC Berkeley 70 years ago. And what Tolman was trying to do was understand if rats were building any representation when they moved around. So what Tolman did was this simple experiment where he took a set of rats and put them in this kind of a maze at location A, that I'm showing you the pointer. And what these rats very quickly learned was, oh, I should go around to the top, then turn left, turn right, and then I'll get to a place. And once the rat got to that place, it used to get food. So Tolman habituated a set of rats in this particular environment. And then what he did with these habituated rats was to place them in a different maze. So in this particular maze, he would introduce them at the same location, but then the direct path that they used to take is now blocked. And what these rats very immediately learned to do was to actually directly go in the direction in which they originally used to go. So this was essentially telling Tolman that rats were not exhibiting behaviorism. They were not going from this, oh, I see this corner, I should turn left. I see this another corner, I should turn right. But they were essentially able to integrate information that they were seeing into a representation of the world that they could do some reasoning on. They could find shortcuts and so forth. So this essentially indicates that that there is something beyond low-level control which even simple rodents like rats are able to do, which is build up these representations that they can do reasoning and planning. And this is essentially what motivates our proposed solution for robot navigation, which we are calling cognitive mapping and planning, also CMP, which is essentially a neural network-based policy for visual navigation. It's a joint architecture which has mapping and planning modules. There is a spatial memory which serves as the representation for space that we are building up over time. It serves as a map. There's a differentiable planner which can plan actions given incomplete observations made in the world under partial observations. And it's obviously end-to-end trainable, which allows us to learn specific concepts specific to the problem that we're solving. So here's an overview of the CMP architecture. We start with this image that you're seeing on the left. This is the current observation. This is passed through a differentiable mapper, which essentially tries to produce a multi-scale belief of the world in an egocentric coordinate frame. And this belief of the world is passed onto a differentiable planner, which takes in the goal and the belief of the world and tries to output actions that the agent must take so as to get to the goal location. And this happens at every time step. At the next time step, the robot executes an action, which results in some ego motion. This ego motion is used to transform the belief from the previous time step into the current coordinate frame, which is now updated with the new observations, and then you repeat this at every time step. So we are looking at this in context of mobile robots. So these are ground robots that want to drive around in the world. So the representation for this world is being generated in this top-down coordinate frame. So think of this as the top-down bird's-eye view of the building that you are in, let's say, for example. This is maintained in the egocentric coordinate frame such that you are always at the center of this representation looking upwards. So that's just a coordinate frame choice that we made. Now I can walk you into different pieces of this architecture. So we have this differentiable mapper, which essentially starts out with this confidence and belief about the world that has been computed over the past observations. And we have these new images that need to be incorporated somehow into this representation. And these new images come with ego motion, what is your relative location with respect to the previous location, and this new image that you're observing. So one part of this differentiable mapper essentially takes in the ego motion, takes in the belief from the previous time step, and transforms it so as to bring it in the current coordinate frame. So for example, if the agent rotated, you would rotate the belief in the opposite direction so that you're again at the center and looking upwards. If you move forward, you would move the representation down. So this is being done in this differentiable manner through this differentiable warping layer. The next component then is to take in the image that you're observing and use this to update the information that is present in this map. So again, this is like an image from the first-person camera that the robot has. You can see this view of the hallway. And we pass it to a convolutional neural network. In this particular case, it's a CNN which has an encoder which takes images from this first-person view and then tries to transform them into this top-down view to produce an update for the map. This CNN is composed of an encoder network, which goes from pixels to like an abstract representation of the scene. And this is often a very semantic sort of a representation. And then you take this representation and convert it into a top-down frame and then start upsampling this in this top-down frame. So the kind of cues that this neural network can pick up are shaped from single image sort of cues. So for example, if you see a chair in the bottom right corner, a big chair, you know it's going to be close to you. You know what kind of pattern it would emit in this top-down view. And this is all some things that you can learn from data. So this is a differentiable mapper component.
Sorry.
Yes.
Is this supervised?
Yeah, this is a very good question. So the supervision is going to come from the planner. So there's no explicit supervision for what the mapper should output. The supervision is going to come from the fact that whatever representation the mapper is generating should be useful for the planning that is going to happen. And that's what I'm going to talk about next.
So
yes?
No self-supervision like the ego motion where you back rotate, for example, plane or the map.
Yeah, so in this particular work, we are assuming we know the ego motion. So let's say, because the robot actually took the action that it took in the last step, so it knows what action it took. So that results in the ego motion. So we assume that we know that. Right, so this is essentially, I walked you through this mapper component, which generates this belief of the word. Let me now tell you something about this planning component. So our planner is essentially based on the idea of value iterations, and this has been around for a very long time. But the basic idea over here is you have a Markov decision process. So a Markov decision process has states, and then there are actions that you can take to go from one state to another state, and so forth. And there's a goal state that you want to get to. So this is a Markov decision process. And the way one can solve a Markov decision process, which is to compute an action at every state that one must take, what we can do is something called value iteration. So you know that going to at the goal location, it's good to be at the goal location. And now you can do this iterative procedure, which is you spread, okay, it is good to be at the goal. So it is good to be one step away from the goal. And it is good to be two steps away from the goal, and so forth. So you do this iterative procedure to estimate how good is it to be at each particular location in space. And this is done through this iterative algorithm called value iteration, which does these two steps. So it wants to maintain, compute this quantity Vn of S prime, which is the value estimate of a given state given some number of iterations that you have done. And if you have done n iterations, you want to compute how will you compute the n plus 1 iteration. And you do this by computing a one-step simulation. So which is that for every state you simulate, okay, what happens if I took this action and then took n subsequent optimal actions. And that's what is this Q-value function, which is a function of both the state and the action. And then once you have this Q-value function, you can max pool over the actions. You can take the best action that you can take possibly at this time step, so as to maximize the return. And that's how you update and get your the value iterate for the n plus 1 iteration. So this is nice, and if you're concerned with an environment which is like a grid where an agent is moving around, then you can actually compute these two equations locally. So when you are simulating the effect of an action, it will only change a location locally. So now all you need to do is to look up the values of your neighbors on this grid kind of a graph, and then compute the Q-value function. And then and the nice thing is that now if you represented space, this grid world as an image, you can simulate this operation via convolution. Convolution involves looking up neighboring values, doing some computation on them, and then updating and producing them. Yes?
So if you do this on real data, where does the reward come from?
Yeah, so I'll get to it actually. So this is essentially the motivation. This is the architecture which allows you to capture planning computation. Now, if you have this architecture, now you can start learning some of these things. And I'll get to it in a minute. That's a good question. So, right, so the first equation you can implement using convolutions, and then the second equation you can implement using max pooling, which is again like a standard operation in a convolution. And this is an observation that was made in this NIF paper called Value Iteration Networks. It is again from a neighboring lab in Berkley. So we can actually look at what this results in. So for example, if you had this kind of a toy maze-like map where you wanted to get to the start location, and you did this operation of doing convolutions and max poolings with an appropriate choice of a kernel, what you get is something like this, a value map which looks like this, which is high in the region where you are, where the goal is, so it's good to be at the goal location. And then it has these gradients which flow away from the goal location, taking into account the different obstacles that you have. So for example, over here you see this dark blue region, which is essentially saying that that this is there's an obstacle here and there's less value to be at this location. And then the nice thing is now you can just compute the local gradient of this value function to compute what are the optimal actions that one wants to take to get from one to get to the goal location. So now, as I said, in our case, what we do is essentially take the mapper the representation that the mapper is outputting, which is this kind of a feature map, and you pass it through this value iteration module, which do some number of iterations of this particular algorithm, which involves doing convolutions and max poolings, and you get something which around you can tell you what the optimal action you should take. So again, as I said, the agent is always going to be in the center, so you take out the value map around the agent, and then try to read off the action that the agent should take. Now, if you have some supervision as to what is the optimal action that one must take, you can start learning parameters in these networks. So for example, if you knew what is the right action to take, let's say via reinforcement learning or imitation learning where you are trying to imitate the behavior of an expert, you can actually start learning the parameters that are there inside this plan. So you can, instead of having to handcraft these convolutions to take into account obstacles and free space and everything, you can actually just learn these convolutions. You can learn the parameters that exist in the planner. You can also, because it's differentiable, you can also compute gradients through the planner into the mapper. So now the planner can actually tell the mapper what is it that it should focus on, what is the representation that it should generate, such that it is going to be useful for planning. And at the same time, you can naturally trade off partial observability. So again, you have not observed the entire environment, but that's fine. You can learn this exploration trade-off with experience. So I think that gets to the question that you were asking, which is that if there is a reward signal, so you can train this with reinforcement learning, where you get a reward after some number of time steps, and that you can backpropagate to learn these parameters, or you could use iteration learning.
Yeah, but in your case, you have this robot being navigating on real data, so it's
Yeah, so
like it's artificial environment that giving you rewards.
So yeah, so I think designing reward functions is hard, but in the real world, it could come from the fact that, oh, I want to get to a particular image which I have stored. Let's say I capture images and I want to say I want to go from one image to another. So the reward can be computed in that kind of form. In this particular work, we are actually training in simulation with imitation learning. So everything is available and you can train. And then we are deploying this to a real robot. And I'll get to that now.
Isn't the reward map learned on its own?
So the value map is learned on its own, but you still need to figure out, okay, what was the good, you still need to learn what the you still need to have a reward function under which you learn value map.
So in the original paper, the reward just at the goal and everything else is zero.
Exactly, yes.
So how are you doing it?
So that's what we are actually also doing, yes.
So you set a goal at every partially observable?
Yeah, so the goal is specified essentially in terms of this kind of a map that you're seeing. It's like a point, or it could be like a semantic target that you want to reach. Like class table, okay, I want to reach a chair. I want to reach a
But that space over there is just the partially, like the space you see right now, or is it the entire map?
So when you say you want to reach a chair, you just say I want to reach a chair. That's it.
Even if you don't see the chair right now.
Even if you don't see the chair right now. So then the reward, problem specification is I want to get to a chair, and then the action that it sees during training is like, oh, okay, getting to a chair led to good reward, and I was supposed to go to a chair. So that's how you learn about chair. There's one additional trick that is required to get this to work is some sort of multi-step reasoning, because a typical planning algorithm takes linear number of steps as to number of goals, steps to goal, and we want to run a robot for a large number of steps. And to make this computationally feasible, what we're doing is introducing an approximation which solves planning problems at different planner lengths. So you solve a coarse planning problem where you are representing space very coarsely, and you kind of figure out, oh, this is the rough direction in which I should head. And then you upsample the planning problem by literally taking the value map, cropping it around the agent, and then solving another planning problem with a more high resolution map. And you keep doing this for computational efficiency. So this has this nice property that space which is very close to the agent, like my immediate space right now, is actually represented at a much higher resolution, and which is useful for planning immediate actions which might actually collide with the different objects and so forth. So this essentially take care of that. So thus what we get is essentially these two modules which we can stack together to now train end-to-end for the task that we are interested in this case, navigation. And what is interesting to note over here is that, that the supervision for the mapper, there's no supervision for the mapper. It's directly coming from the planner. So the planner is able to tell the mapper, okay, this is what I care about, this is the kind of representation that you should learn, and this is the task-driven representation, which is now could be anything. It could actually be free space, maybe free space is useful, or it could be other semantic concepts that are useful for navigation. And we are not handcrafting these are being learned from data. So now I'll walk you through a set of experiments that we did to test out some of these ideas. So for the set of experiments I'm going to describe next, they are trained and tested in static, simulated real-world environments. I'll get to this in a little bit. And the testing environments are actually different from training environments. So we work with scans of buildings, and we are training on scans from 2 buildings, and we are testing on a scan from a 3rd building. So there's clear train and test division. We have abstracted out some of the properties of the robot. So it's like the robot lives in a grid world. motion is discrete. It can either go forward, turn left, turn right, or stay in place. There are these macro actions. Robot has access to its precise ego motion. So it knows what action it took, and it assumes that the action got executed perfectly. We can study this in context of RGB images or depth images, and we have experiments with both of them. Model are trained using Dagger, which also I'll get to in a minute. And then we have two tasks. One is a geometric task where you want to go to a particular point in space, and there's a semantic task where you want to go and find chairs, doors, and tables. So to give you a sense of the data that we're using for this, this is actually from a CVPR paper last year, where they scanned a set of buildings at Stanford, and these are kind of renderings from this kind of a simulation environment. So it's a real-world environment that has been captured, and now you can render it and now reproducibly train models, test models, and compare different models and so forth. Useful from that perspective. Now I can tell you a little bit about policy training. So in principle, we can train these networks using reinforcement learning, but what we are doing in this particular paper is essentially convert it into a supervised learning problem. So we assume that we have an expert who knows how to solve this problem. And this is not hard to assume in a simulated environment like the one that we're using, where you can compute optimal trajectories using graph search algorithms. And so what you know at each state is what the expert did. So what is the right action to take? And that is where we are computing supervision from. Except that there is one small caveat that if you were to just do this, you were to just take expert demonstrations and try to mimic those, you run into this data mismatch problem, which is that you will never be able to mimic the expert precisely. So for example, in this case, as you're driving along, you will go off course. And then if you've gone off course, then you actually never saw what off course, what does it mean to go off course. And then you don't know what the right action to take. And this you can fix with using dataset aggregation, where what you do is essentially re-query the expert. So if you think you have gone off course, you ask the expert again, okay, what is it I should do in this particular situation? And you keep doing this a few times. So you create a policy, you try to run that policy, you see you are going off course, you ask the expert again, what should I have done? The expert tells you what is the right thing to do, you get more supervision, you get more data, you now train a better classifier. And you keep doing this a few times till you actually converge. Right, so now here are some results. So in this particular case, this is a geometric task where you want to go to a particular location. We experimented with both RGB images as input and depth images as input. And what we can, for example, look at is this success rate. So higher is better. So the key comparisons to make over here is, one is to this reactive method, which is essentially this feed-forward representation, which does not build up a map of the world or anything. And that performs poorly with about only 30% success rate. Then we can also compare to, you can augment these networks with memory of a vanilla kind. So it's like an LSTM-based memory, which you put on top of this feed-forward network. And that does lead to improvements in performance, which goes back to the point that, yes, you want some localization to the environment that you are in. But then using fully spatially aware representations, such as the ones that we proposed, you get even better performance. Another key comparison to make over here is a comparison to a more classical way of solving this problem, wherein what you do is analytical mapping. So you throw away all the semantics. The mapper essentially sees only the depth images that are being observed, and you project those depth images into this top-down view. So this is the map that a traditional approach will build up using the observations that we're using. And then you can use it again with the same planning scheme, and everything else remains the same. And what you see is a performance of 62%, which is, again, much worse if you were to use the depth images directly for training. Which again goes on to show that the role of semantics in trying to solve these navigation tasks. We have some additional comparisons between LSTMs and CMP. There's better generalization, larger improvement for longer horizon tasks, better performance on hard trajectories, but I'm not going to all those details. There are also ablations that you can do. Yes, single scale planning works almost as well, except it is slower. You can remove the planning module, but then that results in worse performance, so all the usual things check off. The other nice thing you can do is you can now start taking this model and teasing out different aspects of it. So as I said before, the mapper is generating a representation, and now we can ask the question, what is this representation good for? So note that we did not explicitly enforce this representation to be anything meaningful. In fact, these are just feature vectors of some dimensions at each particular location. And what you can do is now, after you have trained this model, train a readout function, which tries to say, okay, can we actually read out different properties? So the property that I'm showing you over here is essentially free space prediction. So one could argue, one could hypothesize that, oh, free space prediction would be something that an agent should be able to do if it were able to, if it was trying to move around in an environment. And that actually ends up being the case. So when we try to train these readout functions, so the top row essentially shows the output of these readout functions. The bottom row shows the ground truth. And this is the scenario that the agent was faced with. So it was inside this room, it started coming out, and then it came out in the hallway. But then if it's able to, it is able to predict this free space behind the door. So it's only seeing part of the door, but it's able to say, okay, there is free space behind the door. So this is essentially indicating that these representations actually do speculation about things that is not entirely seen right now.
So the initialization points are different points.
So this is the trajectory that it executed. So it started from being inside this room and it wandered out.
For the first image, which is the point where it's...
Yeah, so the agent is at this. So it is the agent at this point is at this triangle.
Okay.
Yeah, and these are the different resolutions. So this is at the finest resolution. This is at the coarser resolution. This is at the even coarser resolution. So you can say, for example, this point A is essentially this point inside this doorway. And note that I'm showing you these top views just for ease of visualization. The agent was actually seeing these first-person images. Then this agent goes down further, it goes into this room, and then you can take the space representation at that point and try to read it off. And what you see is something like this, where this hallway, which is outside, is clearly represented by this. So, and I mean, you can do the same thing for other semantic categories, but you can also visualize the output of the planner. So this is, for example, what the value map looks like at different time steps. I'll not go into too much detail over here, but then you can actually rationalize the behavior of the agent given these value maps. So in this particular case, it wanted to go to this green star over here. It started out and then thought I should go up into this room and then come down, but then it realizes that that point is probably not in that room, so then it backtracks and starts coming out the other way. Here are some successful navigation examples. So in the top row, I'm showing some easy cases where you just do the usual. You want to go from the blue dot to the green star. So you walk along, make sensible use of hallways and get to the target location. In the bottom row, I'm showing some backtracking examples where the agent actually is able to backtrack. So it, for example, in this particular case, it goes up till this point and then realizes maybe it is not in this particular room but in the other room, and then backtracks and comes back. And this is again behavior that purely feed-forward network will just not have. And whereas an expressive architecture that as the one that we are using is able to exhibit this kind of more intelligent behavior. We can also study semantic tasks, as I was saying. All that changes is the supervision. So you just swap out supervision for going to the point in space, but going to like an object of interest. So in this case, nearest chair or nearest table or nearest door, and you can run the same system again, which is in departure from traditional system, classical mapping system, which will have to bake in a lot of these object detectors and everything. But over here, everything can be done implicitly. Here are category-wise results. It doesn't do as well as the geometric task, but it's a big need. Here are trajectories for getting to different semantic tasks, which I'm not going into too much detail. What we have subsequently done is tried to run this on a real robot. And in this case, this is just version 0 of this thing, where we take the policy that was learned in simulation on these realish looking environments, and then just deploy it on a Turtlebot where we are just running these. And in this particular example, the goal was, in the top example, the goal was to get 5 meters ahead. So it's like after these kind of chairs, and what you can see is it is able to successfully not bump into chairs and move till actually it reaches the target location. In the bottom video, what you're seeing is essentially it wants to go out of this cubicle area, so go forward 4 meter and right 4 meter. And I mean, we artificially created this, or place this chair so that it cannot go directly, so it finds its way around these obstacles. And this is somewhat surprising because I mean everything was trained in simulation, and we are just running it in the real world. So glad that it works to some extent. Here are some more examples where again it's able to do collision avoidance and it's able to move around easily.
What kind of computer you're running?
Yeah, so this is actually the laptop that we have kept on this Turtlebot, which has a high-end NVIDIA GPU. It's like a NVIDIA 1060 something. and it can run convolutional neural networks. But if you were just doing inference, we can actually run it on TK1 and so forth as well, but we have not tried that.
This is the roughly the frame rate, or what's it?
The frame rate is actually much higher than this. I mean, in this case, we have a low-level controller that we implemented, which executes these macro actions. So rotate in place, go forward, and rotate right. The slowness is because of that controller and not because of perception. So perception is actually, like doing a forward on this kind of a model takes, I think, 15 milliseconds or something. Right. Here are some more videos which actually show backtracking behavior. So this is in simulation. So what you're seeing on left is some backtracking behavior. So it goes straight and then realizes that it's not the room, comes out back, and then goes into this other room where it actually finds where it was trying to go. On right is this semantic task where it wants to find chairs. So it misses a few chairs, but then it will finally go into the conference room, and then there are lots of chairs that will declare success by rotating in place, and I'm at a chair. Here's another example which it wants to again find a chair. It is in a hallway, and it decides, oh, I should just go into a room and find a chair over there, and that's what it does. Rotate in place. It has some more videos which I'll skip in interest of time. Here are some of the failure modes. So at least in simulation, there's like quantization artifacts that you're not able to move out of tight spaces. Then there are these missed pathway effects that you thought it would be in the room on the other end of the corridor, but then it turns out to be a big room. So mismatch in statistics. And then occasionally there is thrashing where the agent is not able to decide what it actually wants to do. So in what I've described to you so far, we have been considering navigation in a static mode. A world which did not have any objects that you had to mess around with to actually move around. But the real world is more challenging, obviously, and you may be faced with a situation where you actually have to move some objects around out of the way to actually be able to move around. And whatever reasoning that I showed you so far was certainly task-driven and spatial, but it was scene-level monolithic reasoning. So there was no reasoning about individual objects. Yes, you could recognize objects, but you could not figure out, okay, what would happen if I applied a force to this object, because the representation was being generated at a scene level. And this is essentially what motivates object-centered scene understanding, which has been obviously the focus of a lot of work in computer vision. And this is what I'm going to talk about next, which is how do we understand scenes with a special emphasis on objects. So you can actually look at other representations in computer vision, and what you find is this kind of a spectrum, which is there are representations which only reason about the image space, so only about pixels that you're actually seeing. For example, you can reason about shape and so forth, but only about the visible objects. But then there are representations which go to full 3D representations. So you want to reason about even extent of objects which you're not seeing right now. As you can see in this top right corner, which is like you want to predict semantic labels for a lot of hidden boxes. Or you could go about doing this in a more object-centric way, but these representations are not very expressive. So what we want to do is essentially go towards a representation which represents objects. So for example, if you are given this image, what we want to do is to replace each object by, let's say, a CAD model of the object. So replace all the chairs that are there with like a chair that from a CAD model. Or better still, you might actually want to represent each chair with like a collection of boxes that you are actually computing specifically for this chair. So you might go beyond just generating CAD level or CAD models. And this is something that I have been, this is of interest to a lot of people in the computer vision community, and this is obviously this is for the focus of a large amount of work that I did early on during my PhD, where I studied these in context of RGBD images so that we can use them in robotic context. So I'm not going to go into all the gory details of this, but just provide a high-level overview. So what we ended up doing was essentially detailed object-centered 3D reasoning via efficient 2D processing, followed by detailed shape prediction. So we know all of these object detectors, they're extremely efficient. They can run at 10 and 20 frames per second and produce localization of objects. But this localization is limited to be 2D bounding blocks in this sense. And this is a good starting point because this is very fast and is presumably useful in a robotic context to be fast. And what we do over here is essentially augment it with other kinds of auxiliary outputs, which we can use such that we can do detailed shape tracing. So this particular work, again, as I said, this is in context of RGBD images, where what we're doing is essentially you start with these bounding boxes, but then instead of just predicting a class label, you also predict like the segmentation and the coarse pose of this object. And this is necessary because what we wanted to do was to use ICP for aligning CAD models. And we know ICP does not work with cluttered scenes and when you have bad initialization. So having a scene and basically predict these segmentation allows you to figure out, okay, this is the part of the scene that I want to focus on. And then also predicting a coarse pose, which is roughly what direction is a chair facing in, allows you to better initialize ICP-like procedure for aligning these models. And this actually works reasonably well with cluttered images from for example, the N by U dataset, where what I'm showing in this case is just the RGB image, but there's an associated depth image. And what I'm showing you is these models that have been placed, and I'm rendering them and showing depth in pseudo color. So you can do one object per scene, you can do multiple objects, and you can look at all these chairs that get replaced fairly well, and you're able to deal with cluttered scenes reasonably well. What I've been subsequently doing is figuring out how we can generalize these to RGB images and not restrict yourself to RGBD images. And again, the philosophy is the same. We start with efficient 2D processing and then augment it with auxiliary losses which can allow us to reason about shape. So in this particular case, what we are predicting is essentially the 3D location, 3D pose, scale, and shape of the entire object expressed as boxes. So this is what you're seeing over here. So we predict the translation, scale, rotation, and the shape code, which you can actually decode into a full voxel representation of the object. And again, this is trained with full supervision on synthetic data. So if you have all of that, then why not train a conment to actually do these tasks? And again, this is trained in simulation, but then we are testing it on real-world images. So in this particular case, again, this is the RGB image. We are not using depth in this particular experiment. And what I'm outputting is essentially voxel reconstructions of different objects that are there and placing them roughly in the scene. So it does something reasonable, but there is more scope to build upon this. Right, so this is the visualization on more scenes. This actually brings me to this last segment of the talk, which is about multimodal representation. So I showed you in the previous part two experiments, one with RGBD data and one with RGB data, and it was very clear that the RGBD version was working much better than the color-only versions. And now this is essentially motivates that in context of robotics at least, where we can put in extra sensors, it is worth looking at representations which can be learned from multiple different modalities. So as we know, robots can be instrumented with a variety of sensors. So it could be depth images, as I was showing you in the experiments in the previous part. But there could be other things like LiDAR data, it could be thermal data, it could be haptic data, or even sound, for example. But then there's this one challenge, which is that there's not enough of this data out there. So for example, because I was interested in depth images, this is the dataset size, roughly in terms of the visual variety in different datasets, and these are 4 popular depth image datasets. Whereas these are a couple of RGB image datasets, which are clearly a couple of orders of magnitude larger than depth image datasets. And this is a challenge because the dominant paradigm for learning features essentially relies on large quantities of labeled data. For example, if you pick a random CVPR paper, it is very likely that it starts with a network that has been pre-trained on ImageNet. And ImageNet is like a data set, 1,000 classes, 1.2 million images. You use this for fully supervised training of representations. And once you have such a representation, now you can start using this representation. If you're interested in the task of object detection, you can take this representation and then start training object detectors and so forth. And now this presents us with a challenge that how do we do the same thing for imaging for modalities for which we do not have such large-scale labeled datasets to be able to pre-train these neural networks. And for this, what we came up with was this idea of cross-modal distillation, where we are trying to steal supervision from well-labeled rich modalities to train representations for less well-labeled poor modalities. The idea here is actually very, very simple. If you look at the representation that a neural network ends up learning, and if you look at the higher layers, they are actually semantic in nature. So for example, here are visualizations of pool 5 neurons from a particular RGB network that was trained on again on ImageNet. And what you see is that it very consistently fires on video faces. Here's another neuron which actually fires on dog faces, and then another neuron which fires on TV monitors. So if these representations are semantic, this can actually serve as supervision for other modalities. So for example, in context of RGBD data, we often have this occurring in pairs. So you have an RGB image and you have a corresponding depth image. And what you can do is essentially run a state-of-the-art whatever ImageNet network that you have trained on this RGB image to obtain this high-level semantic representation, and you use this as a training target for representation that you want to learn on this new modality. So you run it through this network, you compute the output, and you use that to supervise the network that you are training on this auxiliary on this new modality. And so now the paradigm becomes you don't need labels, you only need large amounts of paired data, which is a simpler requirement to meet. And the pipeline then becomes you pre-train your image representation on a large data set like ImageNet. You have your robot go around and collect paired observations in these two different modalities. And you use cross-modal distillation to transfer supervision from RGB images to depth images, or your modality of your liking. And then you start using this representation by fine-tuning it on the tasks that you actually care about. And this learned representation works surprisingly well. It helped us achieve state-of-the-art results on different semantic tasks on the NYU depth dataset. Interestingly, features work well by themselves, but you can also further fine-tune these features for the tasks that you are actually that you actually care about. Features keep improving as RGB networks improve. So we did these experiments with AlexNet, but then VGG and ResNets came along, and you can do the same experiment, same transfer with these more expressive networks, and you get better performance. At the same time, there is still room for these representations to be complementary to the original RGB features, because if you start off with these features, they can actually go off in a different direction in which it can start leveraging the complementary aspects of the new modality more naturally. And note that you don't just get a feature, you get this entire feature hierarchy. So you get good features in all these underlying layers, which you can actually use for fine-grained tasks like segmentation and so forth. And they help as much as what RGB networks have been shown to help. And interestingly, since we put out this work, other people have actually used this in lots of different interesting contexts. So there are papers which are trying to do this distillation for learning representation on these sphere images, which you get from panoramas. There is work that has tried to use this in context of when images undergo degradation because of noise. People have also started taking a look at this to transfer supervision between different modalities. So training a network for sound recognition based on the fact that audio and video coexist. So you can transfer supervision from ImageNet to learn representations for sound. You can also learn representations on on voxels, on volumetric data, and then transfer it so that it starts working on image data. People have also applied it in context of learning image models, which you can take supervision from, let's say, English for a task that you can now want to do in German, and so forth. Another thing that such a representation gives you for free is aligned multimodal representations. So what I'm showing you is this neuron number 5.201 in this particular network, and this neuron seems to like parts of chair legs. And you can look at the same neuron in the depth network, and it also likes parts of chair legs, but in this different modality. There is another neuron number 107, which likes parts of bed, so it likes like large flat texture. And again, it is shared between, it is the same neuron that will fire on the same things on the depth side. So what this allows you to do is zero-shot depth-based object detectors. So what you can do is you can transfer detectors between modalities without needing any additional annotation. So you can start with the RGB object detector, which you can build using large-scale publicly available datasets. You can take the network, you can partition it so that, oh, here is a feature extractor, and oh, here is a classifier. You can take out the feature extractor, do cross-modal distillation with it using paired data, and plug it back in. And now what you get for free is essentially a detector that can work on depth images. And this is just practically useful. So now, I mean, if, for example, you have in a privacy-preserving hospital setup where you still want to use object detectors, where you don't want to use RGB images but only want to use depth images, you get a good starting point, which you can use. I think with this, I'll end my talk. I talked about representations for robotics, which are task-driven, structured, multimodal perceptual representations. I showed you these representations over the course of these 3 projects. I talked about robot navigation, where I talked about how we can build task-driven representations for space. Then I showed you some work on scene understanding, where I showed how we can build object-centered representations. And then I finally showed you how we can transfer supervision between different modalities. Thank you, and I'm happy to take questions.
Time for last.
Yes.
Go ahead, Tom.
I'm sorry, I'm gonna ask you this again. Can you go back to your Untitled Chapter? Back to that slide.
The planning part?
Yeah.
Sorry, yes,
The
sure.
one where you have scale 0 and scale 1.
Yes.
Okay, so the blue thing on the top left and the blue thing on the top right.
Are slightly different, yes.
Yes. Are they the representation of the entire map, or?
So this is, yeah, so this is essentially, you want to go to this, so this is specifying the goal. So you want to say you want to go, you are at a center and you want to go to this breadcrumb.
Okay.
So that's all that this map has. It does not have the map, it only has this point that you want to reach.
But it's a representation of the entire space.
Yes, so in the geometric case, this is the representation. For the semantic task, this is just a 3 vector. Because essentially you want to reach this way, the 3 vector, but the category, you want to reach a chair, table, or a room.
And then what's the other one?
So the other one is at a coarser, at a finer resolution. So this is essentially the representation of the goal and the resolution at which this planner is appearing. You don't see the goal in this representation at all. So the goal is only being seen, I mean, in whatever scale, the goal will be seen only in that scale. And then you compute these value maps, which get passed on to this coarser, into this finer plan. And that is what, so if it's a very far away goal, it will only be visible in like a very coarse scale. It will not be visible at the fine. And that's fine because information can flow through this value map that will be passed between these different scales. When you want to go to a chair, then both these things are just not there. It is just a key vector that you want to go to a chair, indicating what is the task. So it's a task specification more than a reward specification. The reward specification is separate outside of this architecture. So you get reward when you get to a chair. Separate.
So yeah, I have a question related to the reward. So I was a little bit confused how it works. So do you just specify the goal, for example, reaching the chair, and that's the only reward, or do you have like some sort of intermediate reward as the robot like tries to navigate and kind of, because if it's only like if you specify this one goal, it's like very, very sparse reward, which probably forces this robot to initially just randomly navigate without like reaching anything at all. And like how do you make sure that like if this environment is really large, how do you ensure that it will ever reach this goal initially without like learning any policy? Because like
Right. Yeah, so this is the typical sparse reward problem in reinforcement learning. That if the reward is sparse, you actually just don't know is there any way to get to the reward, and all you can do is try out random things. So in this particular work, we are not using reinforcement learning, but we are using imitation learning, where as an expert, the expert kind of knows how to find a chair in an environment. So now what we are learning from is this dense supervision that the expert is providing. So whatever action the expert took, we said, okay, this is the optimal action to get to a chair. So in this particular work, because we wanted to factor out all these different parts separately, so we were just focusing on the architecture. So we said, okay, let's assume we have dense signal, such as from an expert, to learn these policies. Now, but there's nothing that in this architecture, because in a reinforcement learning setup also, all you need is like a policy network, which outputs probability of different actions. And then you essentially run it for a long number of steps, and then you try to do credit assignment. Oh, okay, I got good reward. Maybe all these actions that I took were good. So you compute gradients on the actions and so forth. So you can equally well train these networks with reinforcement learning, but in the work so far, we have not done that. And when we actually try to do it with reinforcement learning, then we will have to address the sparse reward problem in some way. There are ways in which you can tackle this sparse reward problem. Hierarchies is one answer, but I'm not sure if that is entirely clear and known how to do it. There are other exploration-based methods which incentivize exploration in some manner, so one could use those. But again, we have not experimented with those in this context. But all those papers can be rewritten with with a more structured policy network that we have. Yes?
what is your expert in this case? Is it like A star? Or?
The expert in this case is A star, yes.
And it has it has full knowledge of the map, or is
It has full knowledge of the map. Yeah.
And does that create any problems that sometimes your expert output actions, which is impossible to expect the?
Yes, so that does happen, and in particular for the semantic task, because when you're looking for a chair, the chair might actually be behind you, but the current observation doesn't suggest that. When the expert says, oh, turn around, and there is this mismatch, and the right way to deal with this is by computing an expert which operates under the information that the agent knows, but that's kind of a hard expert to even construct. I think another way to get at that is by starting to use reinforcement learning with some reward shaping, where such a behavior is more easily obtainable, or using something like guided policy search. Again, I'm not trying those in this context.
So another question, so here you have a pretty clear idea, this is a 2D space and you want to move from a 2D domain. One with an action is a much bigger space, let's say robot with the grass, but with the move, the dimensions expanding quite rapidly.
Yeah, so I think the planning can actually still be done in a relatively low dimensional space. But then what you're trying to read off is a more complex behavior. So for example, if I were to do this for quadcopters, we probably don't need as many bins in the Z dimension. We maybe need like 4 bins, like cubicle wall, door, ceiling, floor. I mean, these are all of our portions. So these are just the different bins that we need. So it can actually be much lower dimensional over there. And then at each feature vector, you can store more specialized information. But then what becomes tricky is how do you train these kind of controllers, like because now you don't have 4 actions, but you have now 40 actions. Or better still, you may actually have continuous control. And then it's not clear how to construct supervision for these things explicitly. So we have some work which we are working with control people to see how we can leverage controllers that exist, which output these continuous values nicely, and we can parameterize them and train through them.
Related to that, I mean, there's also the action of sensing is an action, right? Where to look,
Yes.
What to use. I mean, are you going to encode that as well in the planner?
Yes, that should. So part of it is being done because of this modeling for uncertainty. So right now we are not just maintaining belief of the world, but we are also maintaining these confidence maps, which encode, okay, what is the speculation and what is the actual observation. And it is possible that this is already being used in some manner, but I don't know, sure. I mean, there was one experiment where we were doing, there was some noise that was being added, and it realized that, oh, if it just rotated around, it would get views from slightly different views, and then the optimal policy ended up being, oh, I should rotate around a little bit to get more information.